Now that we've seen the very basics of implementing an ODE solver like ODE 4.5 in MATLAB, let's take a minute to see what is it actually doing? How is it solving our ordinary differential equation? How is it doing this numerically if it doesn't know how to do calculus? Well, most ODE solvers, or at least many ODE solvers, are using some form or some backbone of the Runge-Kutta or Euler method for solving ordinary differential equations numerically. So let's go through the very basics of how this works. It is certainly more complicated than this, but this is going to be the broad strokes of what it's doing in the background when you ask to solve an ordinary differential equation. So the basic premise of how a numeric solver is going to work is it calculates a value of x only at those discrete time steps that either the software is determining or that you have told it to use beforehand. And what it does is at every step, it knows the value of your variables, and because you're telling it the first order ordinary differential equation, it also is able to calculate what the derivative is at that time, specifically the time derivative at that specific time. So what it's going to do, and this will be illustrated in the next segment, is that if we know our value of our dependent variable at a specific time, and now we are calculating its time derivative at that same time, it's basically going to extrapolate out a straight line from our current value forward to our next time step to make an estimation of what the value at the next time step is going to be. It then takes that next time step as being correct, and it's going to repeat this process over and over again until it's gone through the entire time range that we have specified. When we see this graphically, it's going to make a little bit more sense of what is it actually doing. So here's the very basic equation that it's using. So if we want to know what is the value of our state variable, let's call it x, at some time k, so this is for the kth step, well, we can calculate that by knowing the value at the previous step, x of k minus 1, plus the derivative also at that same previous step, times whatever that time difference is going to be, our time step, which I'm here calling delta t. So it's our previous value plus the derivative times time is our estimate at xk, the next time step. Now, if we want to know the next time step, well, relative to the next time step, the one we just figured out is xk minus 1. So we know our value at that time step. We can compute its derivative because that's what the state equation gives us. We can then multiply it by the time step, and that will give us the next one. So we can keep repeating this as we go forward. Now again, we're not getting a closed form solution. We are only getting this discrete collection of x values that match all of the timestamps, which are determined by all of these time steps, delta t. So the computer doesn't know anything about calculus. It doesn't know how to actually solve these ordinary differential equations for us. It doesn't know the different tricks that we went through in our ODE class. It's doing some implementation similar to this. It's going to be fancier than this. It's going to be more complex than this, but this is kind of the basic premise, is it goes step by step, and it's going to be computing what the next value is based on the previous value, and based on knowing what the derivative is that we give it when we give it our state space model. In general, it's going to be the case that if we have a smaller time step, that smaller that delta t is, the better our solution is. Because we are doing this extrapolation, the smaller we're trying to extrapolate out, usually the less prone to error we're going to be. Now, when we are dealing with linear systems, we can go to pretty small time steps, get a very accurate answer for it, and we can be satisfied that to some margin of error, the solution we're getting numerically is going to agree pretty close to what the closed form solution would yield for us. However, if we're using an ODE solver on a nonlinear system, that's not always going to be the case. Depending on the routine we're using to do our solution that's implementing our solution, even a very small time step might still give us really, really big errors. So just be aware if you encounter especially a nonlinear system the answer you get out from using an ODE solver is not necessarily going to be accurate or good. You have to be careful when using these numerical solvers. So it's going to depend on the complexity of the ordinary differential equation. Even for linear systems, as I talked about before with the different ODE solvers available, like ODE 4.5 versus 2.3 versus 1.5s, if we had, even in a linear system, a very stiff system, we might not get a good solution, or we might never get to a good solution using kind of the usual ODE 4.5. And if we have a nonlinear system that's very complex, we might not get to a solution or not ever get to a good solution using one routine over another. Now again, this is in very broad strokes how the ODE solver is working. It's not going to be using this exact formula. Something like ODE 4.5 operates in a much more optimal way. It is choosing the time steps, usually in an optimal way to reduce the number of repetitions it has to do, and it's doing error checking along the way. It's going to be doing multiple things that are much more complex than just this simple example we're going to look at next of really first manually implementing a Runge-Kutta method and then implementing a very simple software version of it. When we use ODE 4.5, it's going to do usually a much better job than the very simple implementation that I'm going to go over in the next two segments of this example.